Hi everyone, we're up to tutorial 10, question 1 part III, which is here. We're looking to describe the process described by e to the power t divided by s. We're going to use Ito's formula. So a quick catch up what we did on the last video. We stated Ito's formula for two variables, s and t, which we need in this situation. And we know that S follows a geometric Brownian motion, which is the start equation here. So we squared this and dropped it in to simplify matters here, and we derived this equation. And after I'd done some calculations, then I realized I probably should have dropped in ds. It's just coming from this start equation here, and got everything in terms of dt and dB. And I said, oh, maybe we'll just do it later in part 3. So that's the next step. I need to substitute this ds into this part of Ito's formula of the ds to get an equation for the change in the process in terms of dt and dB. So I'm going to do that, and then I'm going to go back to the question and look at the process more carefully and fix this f. Okay, so it's a bit messy on this page, so I'm going to scroll down, find a clean spot. That was the last one, so let's delete that. Okay, so I'm going to sub ds, which follows geometric Brownian motion, into equation 1. And this gives df, which now depends on two arguments. Okay, there's going to be two extra terms. Okay, I think, let's just write it. There's two extra terms, so I think one of them might cancel. Yeah. Oh, that's the wrong equation. No, there's two extra terms. Okay, that's fine. So let's drop them in. So we have this times this. That's the extra term. And now this other term, the dB, I think I'll come down a line rather than squash it on. And there you go. So that's the simple substitution. I shouldn't use the word simple. It's just a slightly long substitution. And looking at the question, it makes sense for us to consider the function f equals e to the t divided by s, because the process, this just matches the process that we're trying to follow. Okay, so the next thing we need to do is calculate all the partial derivatives. So let's take a look what we need. We need this one, this one, this one. Okay, they're all the partial derivatives. So let's calculate those. So we have df dt. Okay, so that is that. Df ds. Okay, so differentiate 1 over s. So it's s to the minus 1. So minus s to the minus 2. So I'm going to take back under. E to this t is just viewed as a constant. That stays where it is. And the second derivative, okay, so minus s to the power minus 2. So 2 s to the minus 3, which goes back under, and that e to this t stays where it is. Okay, so that's a bit of differentiation. You can assume everyone can do that. I think that was studied in year 1 in Math 102, unless you're from, no, everyone would have done that. Yeah, Math 102. Okay, so let's substitute them in. So we have dy, if you like. I think I'm just going to call it this thing. Let's drop them in. So we have df dt, which is e to the t big S of t plus mu s of t, that's df ds, which is in the middle. Okay, just do it like this. And in the third term, we have d2f ds squared, cubed, I should say. All that is dt'd. Now the next term, df ds is minus e to the t s squared of t. I'm going to put the t in there because I'm going to put the t in the other term. Okay, I think that is looking right. Yep. Okay, so that's the process. We just need to remove s of t and simplify. So let's take a look, closer look. Okay, so where can we see cancellation? Well, I suppose I should be aware that y, our process, is e to the t over s squared of t. So this is what I need to be aware of. So I can put in this in various places. Okay, I'm going to cancel one of those. I'm going to cancel those. I'm going to cancel those. Oh, that's handy. I've got e to the t over st appearing in many places. So we have this term factorizes. This comes out as a factor. We have the second term is minus mu. The rest of it comes out as a factor. The next term, all those 2's are going to cancel. Just notice that. So we have a sigma squared and everything else comes out. Just bring that a bit closer. So I can fit it all on. Okay, there's a minus coming out there. Sigma, a y, and a dB. And there we go. There's our final answer. So let's just put it in a box so it stands out. And there we go. That completes the question. Let's just quickly review what we did. We built this equation from Ito's formula, or Ito's lemma, plus the geometric Brownian motion. We studied the case where f was equal to e to the t over s because it matched the question, the process in the question. We did a load of partial differentiation because it appeared in Ito's formula, plus the geometric Brownian motion substituted in. So we substituted the partial derivatives in, and we simplified, and that was our final answer. So there you go, that completes the first question.